In this video, I'm going to show you the second way of the second problem using delta H and delta S to calculate delta G. So in the last video, we just did one example. Here's another example of the same thing. Again, we're going to go through the same process of first calculating delta H, and I give you a table down here with some of the values. So for the first part, we're going to be using this column here and this column here. Okay, and the formula is going to be that delta H naught is going to be, again, it's products minus reactants, so 2 times the delta H of formation of the Fe2O3 plus 8 times the delta H of formation of the SO2 minus, now I do my reactants, so I have 4 times the delta H of formation for the iron 4 sulfide plus 11 times the delta H of formation of O2. Okay, so now I'm going to plug in my numbers from that table below. So it's going to be 2 times a negative 825.5 plus 8 times a negative 296.8 minus 4 times a negative 171.5 plus 11 times 0. Okay, so delta H naught for my products. My products are a negative 4,025. Can't even copy my notes here. 25 minus the reactants are a negative 686.0. So my delta H naught is a negative 3,339 kilojoules. Okay. All right. Now I'm going to do the same thing to calculate the delta S. So my delta S naught is going to be 2 times S naught for the iron 3 oxide, iron 2O3, plus 8 times S naught for the SO2, minus 4 times the S naught for the iron 4 sulfide, plus 11 times S naught of the oxygen molecule. So this time I'm going to be using these columns of numbers. Okay, and yes, these will be given to you much like it is in this problem here. Okay, so it's going to be 2 times 87.40 plus 8 times 248.1 minus 4 times my 52.92 plus 11 times 205. So the delta S for my products was 2,159.6. For my reactants was a positive it's minus, but the products are 2,466.68. So that means that my delta S naught is a negative 307.08. Again, that's in joules per K. It needs to be in kilojoules, so I divide by 1,000 or move the decimal place 3 to the left, so it becomes a negative 0.307.08, and that's now in kilojoules per K. And now I use the delta G naught as the delta H minus T delta S naught. So my delta G naught is going to be my negative 3339 minus, again, the temperature is going to always be 298 for this, so 298 times my negative 0.30708. I realize I had 2 decimal places there. And when I do that, I get a negative 3247.9. Okay. Let me go back and check, because I wrote down a slightly different answer here. So let's see. If I have 2 times a negative 825.5 plus 8 times a negative 296.8. Yeah. I thought I had made a mistake somewhere. This was 0.4, so this is 0.4. So this becomes 0.4, and then that answer is in kilojoules. Okay. All right. Next slide. So just like we did with delta S and with delta H, you can actually find the free energy of formation, or Gibbs free energy of formation, which is the energy that occurs when 1 mole of substance is formed from its elements at a specific temperature or specified temperature. And that's actually the equation at the very bottom of the slide. I'm not sure why. Okay, so again, it's basically the same thing. This is going to be the sum of the delta G of formation for products minus the delta G of formation for reactants. Now, we use delta G or free energy to determine the spontaneity of a reaction. So when delta G is a large negative number, which means a negative 10 or more negative, it's spontaneous as written, so there's mostly products present. When delta G is a large positive number, which means greater than 10 kilojoules, then it's non-spontaneous. When it has a small negative or a small positive value, then it's at an equilibrium in which both reactants and products are present. Okay? And so in the next video, we'll actually do the same 2 examples that we just previously did, but using the delta G of formations.